So today we are in the practice assignment sessions for the course contents covered in week 9 for signals and systems. So let us begin the session for today. First question: if a periodic continuous time signal with fundamental frequency omega naught and Fourier series coefficients ak is input to an LTI system with frequency response h of j omega, then the Fourier series coefficients of the output will be dash. So we have a system, we have an LTI system. The frequency response of the system is h of j omega. Now for the input we know the Fourier series coefficients and the fundamental frequency. Now we are asked to find what will be the Fourier series coefficient of the output.
Option B.
Okay, there is a small thing. It's actually option C. So we will get h of jk omega naught. So let us see how do we get option C. What is our input x of t in terms of Fourier series coefficients? It is summation k is equal to minus infinity to infinity ak e power jk omega naught into t, where omega naught is the fundamental frequency, which is 2 pi by t. And our different AKs, Fourier series coefficients, can be found by the following. So 1 by t integral over t x of t e power minus jk omega naught t into dt. Now what we need is y of t is equal to x of t convolved with h of t. We know that. So when we have a system with impulse response h of t, and if what will be the output is, the output will be convolution of x of t into h of t. And with respect to Fourier transform, basically, we know that if we convert this into Fourier transform, we know that y of j omega will be x of j omega into h of j omega. So the convolution in time domain will be multiplication in the frequency domain. Now, we need to know what is x of j omega. So x of j omega will be summation of 2 pi ak del of omega minus k omega naught. Okay. So now instead of x of j omega, we will write the transform of the input, and then instead of h of j omega, now what you will be getting is j k omega naught, because here we have del of omega minus k omega naught. So this will be valid. So we can think of it as like multiple impulses. So this was valid only at every omega equal to k omega naught. So now this omega here for h of j omega, we have to write it as k omega naught. So you'll get h of j k omega naught. Finally, it is y of t will be summation k is equal to minus infinity to infinity ak into h of jk omega naught into e power jk omega naught. So basically, the the Fourier series coefficient of the output will be ak into h of jk omega naught, because here these impulses are valid for every k omega naught. Is it okay? We're moving on to the next question.
Yes, ma'am.
For a periodic signal with fundamental period t equal to 4 given by, so this is the signal. So x of t is equal to t minus 1 for 0 less than t less than 1. It is 0 for 1 less than t less than or equal to 2. It is t minus 3 for 2 less than t less than or equal to 4. We need to find the Fourier series coefficient A naught. I think in this session we will be covering how to find the Fourier series coefficient, then the basic transforms that you need to remember. It is the basic properties. All those will be covered in this session. So I'll go slowly since we are recording this session. Like I will leave some time for the question, and then when I'm explaining the solution, I'll try to explain in detail.
Okay, ma'am.
Yeah. So now we have to find the Fourier series coefficient. What is our formula? So x of t is summation k is equal to minus infinity to infinity ak e power jk omega naught into t. So ak e power jk omega naught into t, where for every ak we have an expression and we have to solve it. So generally to find a naught, it is very simple. So generally ak, how do you find? It is 1 by t integral over t x of t e power minus j k omega naught into t into dt. So whatever a k you have to find, that k we have to substitute in this formula. Okay. So a naught, when we are finding, it's just direct integral. So if you find a naught, k is equal to 0, right? So it is 1 by t into integral over t x of t. If you put k is equal to 0, that entire expression goes to 1. E power 0, so it goes to 1. So it's just, so to find a naught, we have to just do 1 by t integral over t x of t dt. So this is the formula. Just whatever we are asked to find, we have to substitute for different ak's. We have to substitute in this formula, put the value of k, and then solve that integral. So now to find a naught, it's just 1 by t integral over t x of t dt. Now we know that the fundamental period t is equal to 4. So 1 by 4, and then we have to split the integral. Totally we have 3 parts and the second part is just 0. So it will just be integral 0 to 1 t minus 1 dt plus integral 2 to 4 t minus 3 into dt. Now you just have to solve these two integrals, substitute the limits, and then if you solve this, we are getting answer a naught as 1 by 8. So what you have to remember here is ak is equal to 1 by t integral over t x of t e power minus j k omega naught into t dt. Maybe you can just note down the formulas so that you get familiar to them.
Yes, ma'am. Yes, ma'am.
Okay. So we are moving on to the next question. Now we have two arbitrary periodic signals x of t and y of t. Their time periods are t1 and t2, having Fourier series coefficients ak and bk respectively. So the Fourier series coefficient of x of t is ak, for y of t is bk. The Fourier series coefficients for 3x of t plus 4y of t will be dash. And what is the condition for the Fourier series to exist? Basically, should t1 and t2 follow anything? Yeah.
Uh, Option C.
Okay. Actually, here it's option D. So I'll tell you how. Uh, Now we have two signals x of t and y of t. So for x of t, what will be the in terms of Fourier series coefficients? It's summation minus infinity to infinity ak e power j k 2 pi t by t1. Same way for y of t, it is bk e power j k 2 by t2. So when we have to find 3 into x of t plus 4 into y of t, it's basically 3 into the first one plus 4 into the second one. And if t1 is equal to t2 is equal to a common period capital T, then we can write this directly as summation minus infinity to infinity 3ak plus 4bk into e power jk 2 by t. But if your T1 and T2s are different, then you cannot directly write it like this. So what I was trying to tell here is when we have 3x of t plus 4y of t, if the Fourier series coefficient of this resultant signal should be 3ak plus 4bk means only it is possible if t1 is equal to t2 is equal to a common period t. Otherwise, we cannot write their Fourier series coefficients as 3ak plus 4bk. We have to compute them.
Okay, ma'am.
Yeah. Okay. Now we have a real periodic signal x of t, whose Fourier series coefficients are ak. What will be the Fourier series coefficients of its even component xe of t?
Option C.
Okay, let's wait and see. So, wait. Okay. Okay, I'll go from this. So, first let us see the time reversal property of Fourier series. So, when we know the formula x of t is summation k is equal to minus infinity to infinity ak e power jk omega naught into t. Now we have to find the Fourier series of y of t, which is x of minus t. So let's see how is the time reversal property here. So since we have minus t, instead of t here, your formula takes minus t. Now we have to put this minus k as some other integer m, or basically k can be put as some other integer minus m. So now this entire formula changes to summation m is equal to minus infinity to infinity. I have put k as minus m, right? So instead of ak, I will be getting a minus m e power j m omega naught into t. So if the Fourier series coefficient of x of t was just ak, for x of minus t, it will be a minus k. Because here instead of ak, now you have a minus m, and obviously the summation is in terms of m variable. So when I have x of t, the Fourier series coefficient is ak. When I have x of minus t, the Fourier series coefficient is a minus k. This is the time reversal property of Fourier series. Now let us see the conjugate property. So we know x of t is same thing, summation k over k ak e power jk omega naught into t. Now we are going to find the Fourier series coefficient of x conjugate of t. So when I'm putting conjugate here, obviously I have to put the conjugate on the right hand side part also. So I get ak conjugate. This also goes to conjugate. So e power minus jk omega naught into t. Now if I follow the same strategy, I put k is equal to minus m. Now this summation goes from m is equal to minus infinity to infinity a minus m conjugate e power j m omega naught into t. So I have to compare this and this, okay? What I can see, the Fourier series coefficient of x conjugate of t is a minus k conjugate. So for x of t, it is ak. For x conjugate of t, we find it to be a minus k conjugate. So there's a conjugate and there is a inverse. So it's a minus k conjugate. Okay. So now how do you write the even component of a signal as? So xe of t, even component is x of t plus x of minus t by 2, right? So what is the Fourier series coefficient of x of t? Ak. What is the Fourier series coefficient of x of minus t? We just now saw it is a minus k. So we have ak plus a minus k by 2, right? Now we have given that x of t is real. So x of t is equal to x conjugate of t. It is real, x of t is real. So in terms of Fourier series coefficient, ak now is equal to a minus k conjugate also. So if I write a minus k on the left hand side, it is equal to ak conjugate, right? So we know that x of t is real. So x of t and x conjugate of t are the same now. If in terms of Fourier series coefficient, if I write ak is now equal to a minus k conjugate, wherein from this I get a minus k is equal to ak conjugate. So I take this expression, I put a minus k as ak conjugate. So I get ak plus ak conjugate by 2. We know that this is equal to real part of ak. So The Fourier series coefficient of even component of a real periodic signal is real part of AK. That's all. Okay. We are moving on to the next question. Now it's a similar question, you just have to follow a similar approach. But here we are finding the Fourier series coefficient of its odd component. So how do we write the odd component as x of t minus x of minus t by 2? So this is how we write the odd component. Now in the same way we can write the Fourier series coefficient. We should make use of the information that x of t is real, and then we have to find what is the Fourier series coefficient of x naught of t. Okay. So we are just following the similar approach. So the Fourier series coefficient of x of t is ak, x of minus t is a minus k. So we have ak minus a minus k by 2. And since x of t is real, we already got a minus k is equal to ak conjugate. So now a minus k, I can write it as ak conjugate. So we have ak minus ak conjugate by 2. So let's write ak as some a plus bi, okay? So a plus bi, and this is ak conjugate. So it's minus a minus bi by 2. So if you see here, we will be getting 2 bi by 2, wherein I'll be just getting I into B. So what does I into B mean here? It is I into imaginary part of AK, right? So the answer is I into imaginary part of AK.
Yes, ma'am. Okay, ma'am.
Now we have a real periodic signal. AK, we get it as 1 plus 4j. A5. A5 is 1 plus 4j. What is A minus 5? We have to use the property of a real periodic signal. Real periodic signal means x of t is equal to x conjugate of t. From this you can get the relation between A phi and A minus phi. So if I know one, we can find the other.
Is that 1 minus 4j option C?
Yes, you're right. So we got it. We got that the information is A minus k is AK conjugate. We know what's A5, so we can find what is A minus 5. It's just A5 conjugate. So it's 1 minus 4j. Now we have x of t whose Fourier series coefficient is AK, and another periodic signal y of t whose Fourier series coefficient is BK. We know what's A5, we know what's A minus 5. We need to find what's B5 if we know that y of t is x of minus t. Y of t is x of minus t. Again, this is quite simple. So what is the relation between B5 and A5? We know A5, A minus 5 also we know.
Is this mean that y and x are even or y of t is a even function of x of t, ma'am?
No, y of t is just time reversed version of x of t.
Okay.
So if y of t is x of minus t, b5 will be just a of minus k. So if x of t's Fourier series coefficient is ak, then for x of minus t it is a minus k directly. So b5 is directly going to be a minus 5.
Okay, ma'am.
Now we have a periodic signal x of t. Again its Fourier series coefficient is ak. For y of t it is bk. a2 and a minus 2 are given. What will be b2 if it is known that y of t is x conjugate of t? That is, the question is for x of t it is ak. What is it for x conjugate of t?
Minus minus k.
So it is a minus k conjugate. Just the two properties what we saw in the starting of the session. So it is a minus k conjugate. So there is a minus, there is a conjugate. So if we need to find b2, it is a minus 2 conjugate. So a minus 2 is 2 minus 3j. Conjugate of that is 2 plus 3j. I'm sorry. So the answer is 2 plus 3j. Okay. Determine the Fourier series coefficient a minus 1 for sine of 3t. We just saw the formula for ak. So in that you have to put k is equal to minus 1 and your x of t is sine of 3t. Okay, let us see how to proceed this. So the fundamental frequency of x of t is 3 radian per second. So omega is equal to 3. Okay. So how do we write sine of 3t as e power j omega naught into t minus e power minus j omega naught into t divided by 2j. So this we can split it as two terms, 1 by 2j e power j omega naught into t minus 1 by 2j e power minus j omega naught into t. Now we know what is our x of t. It is summation k is equal to minus infinity to infinity ak e power jk omega naught into t. So we know that k is equal to 1 here, what we want, and then we need a of minus 1. So we can directly write it as 1 minus 1 by 2j. So actual way is to find using that integral of ak. In other words, if we are able to split it like this in terms of exponentials, then you can directly try to solve. So basically we wrote it in terms of exponential. Then we know this equation x of t is summation k is equal to minus infinity to infinity ak e power jk omega naught into t. From this we compared these two, we compared 1 with this, and then we got a minus 1 as minus 1 by 2j. It's a kind of similar question, but not exactly. So now we have a into x1 of t plus b into x2 of t. Okay, where for x1 of t the period is t1, for x2 of t the period is t2. The Fourier series coefficient is possible to find for which case? For which case can we find the Fourier series coefficient for this sum of two signals?
Option A, ma'am.
Yes. So it is possible to find only when T1 by T2 is equal to M, that is, it's rational. Okay. Now we have a time shifted signal x of t minus 3. What will be the Fourier series coefficient? So for x of t it is ak, okay? What will it be for x of t minus 3? Basically we have to find the property of time shifting. If it is t minus t naught, what will we get? It is similar to Fourier transforms.
Option A.
Yes, you're right. So x of t minus t naught's property will be ak e power minus jk omega naught t naught. Okay. Now I think it's kind of repetition. So we have x of t, and then we have a system that's h of t. What is the Fourier series coefficient of the output? So for x of t, if the Fourier series coefficient is ak, for the output it will be ak into h of jk omega naught. Okay. We saw the derivation in the first question. So the answer is B. Okay. The Parseval's theorem is used to measure dash of a periodic signal, and the resultant value of the periodic signal gives dash.
Option D, ma'am.
Parseval's theorem is used to measure the energy actually. So what does Parseval's theorem state is, it states that the total energy computed in the time domain must be equal to the total energy computed in the frequency domain. That is the Parseval's theorem statement. So basically it's a statement of conservation of energy. So if you find the total energy in the time domain, it should be equal to the total energy in the frequency domain. So Parseval's theorem is used to measure the energy, and the formula is like this. In the frequency domain, it is summation k is equal to minus infinity to infinity mod of ak square. Okay. Now let us see basically the MATLAB implementation of Fourier series. Here nothing, I will just share this PPT with you guys. So basically I have written the entire formula how to construct the Fourier series. So to just give you an idea of what I have written. So I have taken t equal to 4, omega naught is 2 pi by t. And what is our signal? Our signal is like this, true signal. So we have, it's kind of a square signal, it's just going on and on. So it's going from -1 to 1, and it's a periodic signal. Okay, this is our signal. So I have written what is x of t. Okay, and I have written the formula to find the Fourier series coefficient a naught, and then for odd terms, and then for even terms. So for even terms it is this one, a sim of n. For odd terms it is b sim of n. Now what I'll do is, after finding the Fourier series, I will try to reconstruct my true signal with the help of Fourier series, and I'll be seeing whether we are able to reconstruct it correctly. That is, I'm having some x of t. Okay, this is my x of t. I found what are my Fourier series coefficients, a naught, a1, a minus 1, etc. Now with this Fourier series coefficient, I will construct a x cap of t and see how close it is to x of t. Okay, this is what I am doing. So if I take just 5 terms, if my n max is just 5 terms, that is 5 terms on the left hand side, 5 terms on the right hand side, just 5 terms if I take, if you see here, this is how my reconstruction will be. So this is my a naught is 0, okay, and my my even terms are given here, my odd terms are given here. And if I try to reconstruct with this a naught, an and bn, if I just use 5 coefficients, just 5 terms, I'm not getting a square signal like this. I'm not getting a square signal. I'm just getting something like this. I have some fluctuations. If I take up to 20 coefficients, I can see a bit more closer to the true signal. Like these fluctuations are reducing. So as I take more and more coefficients for A0, AN and Bn, more and more terms, I can reconstruct my original x of t. If you remember, we have summation k is equal to minus infinity to infinity ak, right? So if I just take 5 terms and if I don't take infinite terms, I cannot reconstruct my true signal correctly. But if I'm taking more and more terms, if I'm adding more and more terms, ak terms together, then I'll be able to reconstruct the signal much better. It is just an idea to, show you that you can find the Fourier series coefficients for any signal. If you just find, right, what signal you want to find, then for that signal, you can, by using the formulas, you can find the Fourier series coefficients. So I will share this code with you. You guys can look into it. Is anybody having any doubts? If no one is having any doubts, I think we can end the session for today.
Okay, ma'am. Sure.
Thank you all.
Thank you.